Hi, welcome back to ATR. Agriculture is one of the most oldest profession in the world, and with 8.2 billion people around the globe, the food demand is at its peak now, and obviously it's only going to increase in the future. But when it comes to producing food, especially in case of laborers, we don't face such a huge issue in India. But that's not the case all around the globe, and that's exactly where agri-tech machinery kicks in. Agri-tech products have grown at an insane pace across the globe within the last decade, especially in India and across the globe. But the problem with India is we still prefer old manual laborers rather than new agri-tech methods. That's mainly because of two reasons. One, we have an insane amount of population to hire as laborers for the agriculture industry. Second thing is the lack of technical knowledge in order to adapt agri-tech machinery. Speaking of which, as robotics engineers, we are not here to cut any human jobs. But the problem over there is the population concentration is very different across different parts of the globe, which leads to critical imbalance of demand and supply across laborers when it comes to countries or regions like EU, US, etc. And this is exactly where automating farms or automating anything occurs. This particular factor is applicable to almost every industry in the world. And in our case, when it comes to automating farms, especially the harvesting part, this is where CropMinder comes to play. Before getting into specifics, let me just clear what CropMinder is. CropMinder is a strawberry harvesting machine with an expandable platform which can also be used to harvest multiple other crops. Now the question is, why strawberries? Even though India is not the biggest consumer or the top consumer of strawberries, but still we are a country which consumes more than 60,000 tons of strawberries every year. Even though we don't face such a labor issue in India, but the countries which produce these kind of crops face such major issue when it comes to laborers. And the thing is, they have already made solutions for that. But those machinery comes above a price range of 60,000 US dollars and well above that. That's basically like above 50 lakhs in Indian rupees. Unfortunately, the Indian farms are not yet ready to adapt to these particular crops based on how these farms are designed in India. This is exactly the gap which CropMinder is trying to fill. We are trying to create a product that's affordable and at the same time with an expandable platform that can adapt to any different terrain and any different farm across the globe. Which brings us to CropMinder Mark II, the second prototype of the CropMinder series. Alright, from here it's pure technicals and the evolution of this particular product and how we made it. So yes, this is how we built CropMinder Mark II.
Hi, let me continue from here. So Joel already gave you overview of what our project was, why we chose it and how we designed it. The first thing was design everything. So we needed to make the actual hardware, but according to what? So we actually visited a farm in South Delhi known as Sara Farms. We contacted them, we went there. It was damn amazing. Organic strawberry farm. So we measured the length between rows, the height and how long the rows are, the dimensions. The design is actually according to the farm which exactly so that it can grab strawberries from both the sides and can touch the ground as well.
Now we had to get started with the concept development. The problem with the concept development is we needed a product that can be used in Indian farms and the farms that are abroad. But the problem over there is in the Indian farms, the strawberry is grown on the ground. And in abroad, the strawberries are grown in racks. So we wanted to create a universal product that can access both the strawberry on the ground and on the rack itself. So based on that idea, I started designing a CAD design where basically I need an unmanned vehicle that can carry almost 30 to 40 kilograms of weight. At the same time, that machine should be having 2 robotic arms to increase the efficiency. I was specific about the length of the robotic arm, which means that one robotic arm have to be at least 50 centimeters in length to reach both the ground and to the racks. So the thing over there is we need robotic arms that can be highly manipulated. That's where we thought about 6 DOF robotic arms, which means that it can be rotated in 6 different angles. We wanted to design the machine in a unique way where it should be able to adapt to the Indian terrains. At the same time, it should run smoothly on the well-maintained farms across the globe. This is where the rugged designing of the machine came into play. So based on that, we used a steering mechanism called Ackermann steering mechanism, which means that we are using a 6-wheel main drive system on the backside and a 2-wheel steering mechanism in the front side. So the gap between the front steering and the second wheel that you see is almost 150 millimeters, around 15 centimeters. That was calculated based on the Ackermann steering mechanism. This steering mechanism is very most commonly used in almost every vehicles that you can see in the market. So we we knew the fact that we have to make this body so strong, so we have to use a proper, very rugged reinforcement frame inside the machine. So based on that, we decided to stick with aluminium. With aluminium is lightweight, at the same time it can provide you enough strength to carry such a huge weight. So based on that, we picked V-slot pipes, which will be very easy to screw the V-slot nuts into it. Along with that, using a V-slot pipe will be easier for us to stick the side panels and the remaining parts onto it. So based on that, I designed a complete framework based on the dimensions which the aluminium have to cut. So as you can see over here, a rough design of how aluminium was supposed to cut and how it's supposed to assemble together was made.
The design is ready. So now we researched all the components are there in the market, which type of motors we can use in the arm. For example, if we have to build a robotic arm, so steppers would be good or the servos would be good, how to control them, everything. The battery pack, the battery should last very long. We then researched about battery packs, whether to choose ready-made or build our own custom battery pack according to the use. The lights, the robot has to function in night as well. We connected lights around it so it looked aesthetically pleasing and also it served the purpose. Then camera, which camera to use, so it has a better quality and the price is decent so that it can detect the strawberries. So microcontroller, we have to run machine learning model, so we chose Raspberry Pi 4 with 4 GB of RAM. So weight of the robot is 30 kgs. We needed really strong motors, so we chose Johnson Motors A grade 300 RPM so that it has very high torque. We didn't go very high speed because it's a farm robot and it has to actually move in the farm.
Now regarding interoperability, so there was this problem over here where we had two robotic arms, and these two robotic arms have to be controlled using two separate Arduinos. The image processing is done via Raspberry. The image processing done via Raspberry is then split to different Arduinos. For example, the Raspberry over here, it's split to Arduino 1 and Arduino 2, which is basically ARM 1 and ARM 2. And later, these values are then again split to a PCA. That's basically a servo controller which can control 16 different servos at a single time. Using that, these servos are controlled using inverse kinematics. So basically, the framework of these two robotic arms were completely sorted out. This is exactly where the problem of communication protocols came in. Okay, so the communication between Raspberry Pi and Arduino have to be done via UART, and the communication via the camera and the Raspberry Pi have to be done via either a USB or even CSI port. So these kind of communication protocols, the communication in between these different components have to be figured out using the system architecture. Because let me explain. The machine learning model is done inside the Raspberry. It uses two different cameras to identify the ripe strawberries. For example, if I have a strawberry in front of me, the camera have to identify the X, Y and Z value of the strawberry in front of me, which is basically the XY is the coordinates of the strawberry within the camera, and Z value is the depth estimation done via focal length mapping of the strawberry within front of me. So these XYZ values, which were later sent to an Arduino using a UART of the Raspberry, and then this particular XYZ value that which Arduino have received, this was used to calculate the inverse kinematics, which was later used to control the robotic arms. And this worked as a loop with a feedback to iterate the process to make the robotic arm reach at that particular point. So this is how basically the robotic arms worked within this thing. And to be very honest, this particular framework is very basic and it cannot be scaled to a larger industrial level. So we are working on scaling and improving the components and changing the components and shifting completely into an industrial grade quality in the next prototype.
So our complete robot is 3D printed. So right now we chose 3D printing, but then we realized if we have to run it in the actual farm, it will be under the sun, so the plastic would melt. So for the structure, we chose aluminum T-slot pipe. They are really sturdy and heavy duty to build with. So the structure is very sturdy. Instead of plastic, we have to use sheet metal from the next time. That's what we learned from the 3D printing. Also, we faced many issues from the printer. If your 3D printer is not of good quality, you will face many issues, and like most of your time will be spent in debugging or finding the issues only. So earlier we bought one 3D printer, Reality Ender 3. It's a very slow 3D printer. It gets damaged really easily. You have to be careful. It doesn't have manual feature. One average print it took around 1 day. Then later we switched to Anycubic Cobra 2 Neo. Amazing. So if you would have known about this, you would have bought it earlier. It's a damn amazing printer. No hassle required. Just plug and play. You have to upload the file and it will automatically level and print it for you. So the file file which took 1 day to print on Ender 3, it took 2 hours for us, which saved us a lot of time. So now we have 3D printed the entire structure. The side panels are ready, the assembly is ready, the robotic arms are ready. So now it's time to assemble everything together.
Oh bhai. Now that's something hot.
So now we have individual parts. We connected the servos to make a robotic arm. So the robotic arm, we assembled it separately. So we assembled each part individually. So we assembled the frame, then we built the outer cover, the plastic side panels, 3D printed side panels. We attached it to it later, and then we 3D printed the tires. We made panel for the tire individually, and then we have different parts so that we didn't fix everything together, because if anything goes wrong, we have to remove everything. Even if one part goes wrong, we have to remove the entire assembly. We have to remove the entire, open up the entire UGV. So now what we did was we assembled everything individually. We assembled one arm separately, second arm separately, and then one motor panel separately, and then frame separately, and then we assembled it all together.
Me using Fleming's left hand rule with the right hand.
Now the Raspberry Pi completely does the machine learning, so it doesn't lack in power. We have Arduino running separately. The bottleneck here is the speed of the Arduinos. Arduino run on 8 MHz only, whereas Raspberry Pi has almost 1.4 GHz of speed. So this thing you have to balance out, so you have to do a lot of research. So if you want to use the Jetson Nano for your processor, or you want to use a Raspberry Pi Pico, like Raspberry Pi 4, Raspberry Pi, a single board computer for the processor, and the Pico to control the arms individually, that's you have to do a lot of research and development.
So Daksh have explained the UGV assembly and the electronic assembly part. Now the R&D expense. We started this project almost 12 months back. That's almost 1 year. Right now I am shooting it on June 11th, 2025. And we started this project on June 1st, 2024. On November, we got done with the first prototype. Right now, on May, we got done with the second prototype. So it was a pretty expensive journey, to be very honest. And the overall cost, which it costed us around $2,300, it's almost 2 lakhs in Indian rupees. The R&D that's done within this particular prototype, which made us learn a lot about how to design a product, how to make the concept into a proper design, how to develop it properly, and how to do different things. Yeah. Till now, it was completely bootstrapped, and later we are planning to do different things with this platform itself. Okay, let me tell you the major mistakes which we learned till the product which we made right now. The problem which we faced was, the first thing is we didn't design a PCB. Okay, that's the most important part of building an electronics product, because you have to design a PCB in order to make the electronics framework and in order to make the entire electronics system to work properly. Not having a PCB was one of the major flaws. Second thing is, the battery was very limited. It only had maximum 2.5 to 3 hours of runtime, even 3 hours and 10 minutes with the extended solar panel. But still, that's not at all enough to run in a farm of a larger scale. The third thing was the issues related with the mechanical side, because the steering mechanism, the front steering part, was not capable of handling such a huge amount of weight when it comes to running it in long durations. Another factor was, it didn't had a LiDAR. LiDAR is a very crucial important factor when it comes to automating products. Even though we are capable of doing it using a camera, but still there are a lot of limitations when it comes to scanning the area and run it smoothly in a field. So we are trying to avoid these mistakes which we made along the way on the next prototype. Along with that, there are many different algorithmic and different other flaws within this thing. We are not trying to exaggerate the flaws, but still it's a learning journey for us. At the same time, we are very grateful for what we built, and we are very happy with what we built right now with a very limited amount of time. And even Dex was telling me the kind of product which we made within a span of 6 months. We completed the second prototype with almost 3 to 4 months gap from January to May. Okay, so that was pretty incredible for us to see what we achieved. So yes, that was the journey of CropMinder Mark 2 and Mark 1. So yes, thank you so much for watching till here. See you in the next one.